Let's look now at section 7.3, and let's talk about finding volume via the shell method. In a previous section, we saw how to compute volume using what's called the disk method. Now, we saw that the disk method and the washer method, which are just two versions of the same thing, have us taking an object and separating it out into disks. Now, if those disks have a hole in the middle, then those are called washers, but it's essentially the same technique, where you have an object, and to find its volume, you're going to slice it up. And you're going to say, okay, let's go ahead and slice this so that it ends up having these little disks that stack together to form the object, like that. So if you pull one of these little disks, and I'm just going to go ahead and pull this one because it's the only one that I drew kind of nice, yeah. Pull this one out, that's a disk. It's got some amount of thickness, but it's a very, very small amount of thickness, a very thin little disc here, like that. And of course, we saw that it's possible to have an object where you have some amount of space in the middle. So for example, you might have something that looks like this. Where you still have these circular cross sections, but in the middle, it's completely hollow. Like that. So this would be hollow space. So if you took one of these thin little discs here and you pulled it aside, you would still have a disc, but since it's hollow in the middle, you would have a hole in the middle. And so this was the washer method. But in spite of the fact that you have that hole in the middle, these are very similar to each other. And in fact, the formulas were the same, except this one required you to subtract away the portion that corresponded to the hole in the middle. Oh, and my camera seems to be set up incorrectly. Let me change that height on this thing. There we go. That's better. Okay. So now today we're going to be looking at a different technique for finding volume. Now we're still going to restrict ourselves to the category of objects where you have circular cross sections, where you create the object by revolving some shape around a region. So for example, this shape was created by taking this object and revolving it, by taking this curve here and revolving it around the x-axis. And this one was made by taking the space between these two curves and again revolving it about the x-axis. And as we saw in the previous section, you can also revolve around other lines. So we're still going to restrict ourselves to the category of objects that look like this. Either start with that and revolve, or start with this and revolve around some line. But now, the way we're going to think about separating our object isn't going to be in terms of disks. It's going to be in terms of shells. You say, well, what do you mean shells? Well, consider a three-dimensional object like a cylinder, like a soda can. Well, actually, maybe soda can is not the best example because those are hollow. So imagine you had a cylinder that's filled all the way through. So maybe think of the soda can with the liquid inside, everything being solid. So you'd have a cylinder, something like this. Okay, so now the cylinder is meant to be solid all the way through. One thing I could do is, of course, I could take a knife and I could start slicing this way, and I would end up with these little discs. But another thing I could do is I could pull out a thin layer of this object. So these are called shells. Notice here, I'm going to push through, and this is made up of several shells, and each one is slightly thinner than the other, and one fits inside the other. But when I fit them all together, they do form a solid object. Here, pretend that's not hollow because I couldn't find one that was small enough to fit in there. But here, well, even if you don't ignore the hole in the middle, this part right here is solid. Right? It's got material all the way through. So here we can think of this object as being sliced this way so that we end up with discs or washers if you don't want to ignore the hole in the middle. But if you don't want to slice this way and end up with these washers, we could always pull it apart this way. We can pull it apart by pulling out layers that fit within one another. These are called shells. Notice that these shells themselves are small little cylinders. Now each of these cylinders is very thin. The walls of it are very, very thin. All right. Now, the height of these, the length of these, is going to depend on the object. If a bigger object will have bigger, longer cylinders. But the thing to note is that the walls of these cylinders are all very, very thin. And even though the cylinders have different sizes, they may have different heights, or they may have a different radius, they all have the same very thin walls. So here, notice I have a regular measurement for the length. I have a regular measurement for the radius of these circles. Notice some are larger than others, some are smaller than others. But one thing that's uniform all the way across is all of these have these very thin little walls. All right. So we are going to think of three-dimensional objects as shells that stack one into the other. And once you stack the appropriate number of them in the appropriate way, you end up with a solid three-dimensional object. All right. So what we want to do is we want to describe how that happens, and not just in words, but mathematically. We want to have a way of quantifying all of this stuff. So let's begin with an arbitrary object and see if we can't find the volume for just one of its shells. Just like we did with the disk and the washer method, once we can describe one of these objects, adding them all together gives you the entire object. So let's describe one of these things, and let me grab one of the smaller ones so that it fits in frame. All right. So here I'm going to draw, and I'm going to have the physical object here just for comparison's sake. Okay, and what I've drawn here is one of these shells, and again, there's nothing inside of it. It's hollow, just like this. That's this object. Now, notice that the thickness of this object is very, very small. Right? It's a very thin wall, but it still has some thickness. So these walls have some amount of very small thickness, which we can call it W, just for right now. So here, W is the thickness of a wall. Thickness of the wall. Okay, well, that's one thing I can describe about this. If I want to figure out how much plastic it takes to make one of these things, I want to figure out how thick it is, right? But I also want to figure out the size, because after all, here, clearly this one takes more material to make than this one does, because it's larger. Well, why is it larger? Oh, because the radius is larger. The distance from the middle to the outside is larger, which makes the whole thing bigger. So I also want to quantify the distance from the center to the outside. After all, that's what a radius is, right? From the center to the outside. So we'll call that P. Why P? Why not R for radius? I don't know. That's what the book uses. Here they use the letter P for the radius of your cylinder. Radius of the base of the shell. Because again, this is not solid, so I shouldn't really call it a cylinder. Cylinders are full all the way through, have a top and a bottom. Here, this is hollow in the middle. Okay, so I have a thickness of a wall, I have a radius, and okay, so now I've measured everything I can about this. I figured out how far that is from the middle, and I figured out how thick the wall is. So now let me turn it to the side and let me measure this other distance here. And that's going to be my length of my shell. So here, we're going to call it H for height, because again, they're imagining that these objects are stacked this way so that you're seeing how tall they are versus their base. So you're imagining this is the ground and here, that's the height. So even though it's laying on its side, we're still going to call this the height, the H. And different shells will have different heights. All right. So now, how do we want to find the volume of this? Well, it's basically just a cylinder. You say, well, it is a cylinder. Well, not quite. Cylinders are not hollow in the middle. They have a top and a bottom and everything inside. Oh, okay, but well, it's kind of like a washer. I start off with a disc. Here, I would start off with a circle. Oh yeah, but there's that stuff in the middle that's missing. Okay, so let me punch that out. So the way I'm going to find the volume of this is I'm going to start with the volume of a cylinder, a big one, and then I'm going to take a smaller cylinder out of it, essentially this. How do I find the volume of a shell that looks like this? Well, find the volume of it as if it were completely full, and then whatever's inside, go ahead and pull that out, and whatever's left, that's your hollow shell. All right? All right, so let's go ahead and do that. Here, I need to point out one more thing. When I say P is the radius of the base of the shell, what radius am I talking about? Am I talking about from the middle to the outermost possible edge or to the innermost possible edge? Because again, notice that's going to be slightly different. From the middle to the inside of the shell is slightly less than from the middle to the outside of the shell. There's a little bit of thickness in there. So here, P is going to be the radius of the base of the shell. It's going to be to the halfway point. So not really on the inside and not really on the outside, but halfway. So it's the radius of the base of the shell to, let me use the same color, to the point halfway along the thickness of the shell. And that'll become important here in just a moment when we actually quantify this stuff. All right, so we're going to have a cylinder. So now forget that that's hollow. We'll worry about the hollow part in a second. Pretend that's completely filled in from the outermost edge to the other outermost edge. Okay, well then recall that the volume of a cylinder has a volume that's given by V equals pi r squared, which is the area of the base, times the height. Okay, so here, forget about the fact that it's hollow, and let's just worry about as if it were full all the way from this outermost shell all the way out to the other outermost shell. Okay, so the height is the height. We're still calling that h. So here, let me just call that h. And pi is a constant, all right? 3.1415926, so forth and so on. So let me leave that as pi. Now you might say, okay, well then the radius is just p, right? Well, not quite. Remember, p only gets you halfway to the outside. It's a little bit further to the outermost edge and a little bit less to the innermost edge. Remember, p is halfway along the wall, not all the way to the outside like we want. Okay, well, the thickness of the wall is W. So if I'm already halfway out, I just need to travel the other half of the distance to get to the outside. P gets me from the center, from the axis of rotation, to halfway into the wall. To get to the outside, I just need to move a little bit further. I just need to move another half of this. If this thing is 1 inch wide and I'm already halfway in, I just need the other ½ inch to get all the way to the outside. So for the larger cylinder, and here I'll say VL for the large one, that's going to be P from here to here, plus that little bit extra, plus half of W squared. Now, what about the small one? What if I don't want to go all the way to the outside? What if I just want to look from the center to the inside? In other words, I want to figure out how much volume I have for that empty space that I'm about to pull out. Okay, well then that's going to be the volume of the small cylinder, which is pi r squared h, which is pi, that remains the same. But now our r is going to be from the middle to the halfway point. Okay, that's P. Oh, but that's too far. I want to go back a little bit. In fact, I want to go back half of the thickness of that wall. So it's going to be P, but then I'm going to subtract away the W over 2. Just like that. Okay, so now what I want to do is I want to take these two and I want to subtract them from each other. So that means that the volume of my shell, so now it's the hollow one, the one where I've pulled everything out of the middle and I'm only left with one of these hollow objects. The volume of the shell is going to be the volume of the large cylinder minus the volume of the small cylinder. All right? If I have this object and I want to get just an empty shell, I want to find the full volume, but then I want to subtract away this stuff that I'm taking out to leave a hollow cylinder, right? To leave a hollow shell. Okay, well then that's going to be pi times p plus w over 2 squared times h minus pi times p minus w over 2 squared times h. Notice here pi and h are common factors, so I can pull that out. That's going to be pi times h times, let's see, that's going to be p plus w over 2 squared minus p minus w over 2 squared, like that. And here I can combine some like terms. Let me go ahead and square everything so that it's easier to see which my like terms are. So let me leave the pi times h outside. If I distribute this out, that's going to give me pi squared plus wp over 2 plus another wp over 2 plus w squared over 4. All right, p plus w over 2 times p plus w over 2. You just distribute everything. But then I'm going to say minus, and then I'm going to do the same thing to this one. P minus w over 2 times itself will give me p squared minus wp over 2 minus another wp over 2 plus, double negative will make that a plus w squared over 4. And now you notice that 4 of these terms subtract away, p squared minus p squared, and w squared over 4 minus w squared over 4, both of those are gone. And then these are all like terms. So I have 1, 2, double negative makes that a plus, right? So 1, 2, 3, 4. I have 4 wp over 2. Which, of course, we can divide the 4 by 2, and that gives us 2wp, right? 2wp times pi times h. So this gives us the volume of one of these shells, assuming that w is the thickness of one of the walls, the width of the wall. P is the distance from the middle to halfway along the wall. Pi is the constant pi that we're used to, and h is the height of each shell. So imagine that you have an object that you're cutting up into these shells. For example, let's say I take this solid object right here, or let's say I take this, let's say I take this solid object that's going to be made by, let's take this region right here. Now this is flat, but I'm about to spin it. I'm about to revolve it around the x-axis, so it's going to form a three-dimensional object. It's the football shape that we had last time. Okay, but now instead of cutting this up into little discs, I'm going to go ahead and slice it up into these shells. Okay, so one of these shells would look like this. Now remember, these are hollow, although the thickness of the wall is some non-zero quantity. Right? Here, this thickness is small, but it's not zero. It's a millimeter, a tenth of a millimeter, something like that. So there is a thickness to the walls, but inside they're completely hollow. Right? One of these objects. Well, now, if I want to describe the volume of this object using these shells, I'm going to have to find the volume of all of these shells. I have to find the volume of each one. Notice some of them are bigger and some of them are smaller. Some of them are wider. Some of them are narrower and so forth. But if I take all of these and add them together, they're going to give me the volume of my object. Okay, so then that means that the volume of my object is going to be approximately the sum of my shells. Okay, so that's going to be the sum as n goes from 1, let me use I. I goes from 1 up to n. We don't know how many shells we're going to have, so here we're going to say starting from the first one, second one, third one, up to n. The sum of these volumes. Oh, well, that's going to be, well, let's see. Each one of these is 2 pi w p h. You say, why'd you say it in that order? Well, because 2 and pi are both constants. Those will never change. But here, the thickness of the wall, the height of the shell, and the radius from the axis of rotation to the midpoint along the wall, those can change. So here, let me write it this way. Let me put the 2 pi first, because those are constants and those will never change. But then all my other variables can change from problem to problem. So I'll say p times h times w. Okay. Now remember what those are. That's going to be the average radius of the base, right? It's not the radius from the middle to the outside or from the middle to the inside, but halfway in between. So a good name for that is the average radius. Here, this is the height of a shell. And this W is the thickness of a shell. Well, notice that the thickness of the shell is very, very small. And notice that here, each of these walls is measured along the y-axis. All right, if I have these shells here, notice that the way I've drawn them, they're laying horizontally, just like I have this object here. How do I measure the thickness of one of these walls? Well, if I measure left to right, that's not measuring the thickness of the wall, that's measuring how long the cylinder is. If I want to measure the thickness of the wall, I'm measuring up and down. I'm measuring that little tiny lip right there. So here, this W is a small, tiny little change in the direction of the y-axis. So let me call that delta y. So this is going to be approximately the sum as I goes from 1 to n of 2 pi p h delta y. But now notice these are dependent on my object, and it depends on the original region that I revolved, which means both of those values are going to be functions of the equation that I have here that governs the original region that was revolved. Or in other words, okay, I know that's a 3D object, but I'm starting with a two-dimensional region, and this right here is a function. Right here I have y equals f of x. Okay, so that function will govern what these variables are. So these variables aren't independent variables, they're functions. Oh yeah, but here my variable's y, not x. Okay, so then maybe I should write this as x is a function of y. Because now I can write both of these as functions of y. So what this says is that the volume of this is approximately equal to the sum of each of those shells added together. And those shells are made up of 2 pi times the average radius times the height, both of which are functions of the variable y, times the little tiny thickness along the y direction, along the y-axis. But of course, that's just an approximation. But if I make these walls very, very thin, then that means that more of them can fit together, which gives me a very smooth edge. So this goes from being an approximation where, okay, these are just blocks that fit one inside the other, but if they're thin enough, the resolution goes up, and here you have not just an approximation, but a perfect replica of your object. And so here we can say, instead of approximating the volume, that's going to be equal to the exact volume if we take the limit as n approaches infinity, as these get more and more numerous, of 2 pi times py hy delta y. But of course, the limit of our sum. But of course, we know what that is. The limit as n approaches infinity of this sum is an integral. That's going to be the integral from a to b of 2 pi p of y h of y dy, all right, our variables with respect to y. And since that's a constant, we typically write it this way. So this is the result of what's called the shell method for finding volume. And that's volume is equal to 2 pi times the integral from a to b of p of y h of y dy. This will be the counterpart to the disk shell method, to the disk and washer method. And the reason I say it's the counterpart is because notice that unlike the demonstration of the disk method that we first saw with this object in the beginning of the first section of the previous section, here, even though it's the exact same object, right, still the same region oriented around the x-axis, revolved around the x-axis, notice that with the disk method, this would have been an integral with respect to x. Anytime your disk or your washer method has an axis of revolution that's horizontal, then you integrate with respect to x. But here, your axis of revolution is horizontal and you integrate with respect to y. These are always going to be complementary to each other. If the shell method uses the y variable, that means the disk method would have used the x variable. If, on the other hand, the disk method would use the y variable, then the shell method will use the x variable. They will always use the opposite variable of each other. That's going to come in very handy because in some cases, it's very difficult to do a computation with respect to one variable, whereas switching to the other variable will make things much simpler. So let's see some examples on using the shell method to find the volume of a shape. We'll start off simply at first, and then we'll see somewhere it's going to become not just nice, but necessary to use this method. All right, so here we're going to have an object that's going to revolve around the x-axis. So we'll start off with the flat region in the plane. This region is bounded by the y-axis, by the x-axis, as you see here. And this curve is x plus y squared equals to 4. Okay, so now we're going to revolve this around the x-axis, which is going to make it look something like this. And that's our solid object. If you're having a hard time visualizing that, that's kind of a bullet shape. It looks kind of like the tip of one of these markers. There we go. That's that shape there. All right. Okay, so we're going to go ahead and find the volume of this using the shell method. All right, well, we know the equation for the shell method. Just like with the disk washer method, computing the integral isn't going to be hard. The majority of the work comes from taking the object and turning it into an equation. Once it's an equation, the integral is usually pretty straightforward. What we want to do is we want to make sure that we turn it into the correct integral, though. So here we go. Volume is going to be 2 pi, integral from a to b, of py hy dy. Okay, so 2 pi is a constant. We don't worry about that. We don't need to figure out anything about that. It's just a number. All right, so now let's talk about our boundaries from a to b. Here, the graph shows that this is the number 2. So that's, 1, 2. And then over here, this is the number 4. So 1, 2, 3, 4. And of course, we could figure that out ourselves by just plugging in some values here. We could say, okay, if x is equal to 0, well, clearly y is equal to 2. Okay, so 0, 2. And if y is equal to 0, x is equal to 4. Okay, so 4, 0. But here, the illustration, they even give us this. This is just one of the problems out of our textbook. Okay, so now, which boundaries do I use? Notice the original object that I had before I started revolving started at the origin. It goes out to 4, and here it goes up to 2. So which boundaries do I have? Is it from 0 to 4, from 0 to 2? Or is it from 2 to 4? Which ones do I use? Well, note right here that you're integrating with respect to y, which means that your boundaries have to tell you the limits along the y-axis. So here, the original shape that you drew before you revolved it started at 0 and went up to 2. Now you might say, well, wait a minute, my object goes all the way down to -2. Right, but we're using the boundaries on the original object. This describes the object that was on the plane, which we then revolved to form the region. These bounds don't describe the total object. They describe the object on the plane which we revolved. So the original flat region. So here that's going to be 2 pi integral from 0 to 2. Right? 0 to 2. We don't care about that 4. It's not necessary. We're integrating with respect to y. Okay, now p of y is going to be the distance from the axis of rotation, which in this case is the x-axis, to the curve that defines your region. Okay, well then that's just going to be the distance from here straight up, or from here straight up, or from here straight up. Oh, okay, but then that's just the y variable, right, of this equation. It's just the y value of this equation. Because after all, what do you call the distance from the x-axis straight up? Well, that's given to you by the y variable. That's given to you by the y coordinate of this point. Okay, so right here, I can use this equation to just give me that distance. Now make sure that you use the equation in the correct format. Here, you wouldn't just write this equation right here. Here, we're writing everything as a function of y. So this would have to be rewritten as x equals y minus, 4 minus y squared. Subtract that over this way. So now this x is a function of y. And that's what p of y is going to be. So 4 minus y squared. Let me go ahead and write that. 4 minus y squared. Notice that if y is... No, wait. That's not right. My apologies. I'm thinking of this one. Here, it's much simpler. P of y, I need something that tells me the distance from here to here. And I need to express that distance using the y variable. Well, that distance is already the y variable, right? If I tell you right here y is equal to 2, what's the distance from here to here? Well, it's 2. If I tell you right here the y value is 1, well, what's the distance from here to here? Well, it's 1. So right here, this is just the variable y. My apologies. I was thinking of this variable. I was thinking of h of y. So here, p of y is going to be, I want to describe the distance from the axis of rotation up to here, because I'm imagining my shells look like this. Okay, so the distance from here to here, I need to express that using the y variable. Okay, well then just call it y. The distance from the x-axis straight up is just the y variable. So now I can say, all right, from here to here, that tells me the radius of the base. So now I need to find this distance across the top, right here, and that gives me the height of my disk, the height of my shell. Okay, well, from here up, that's the y variable. From here across, that's the x variable. Okay, so I could just say that's x, right? From the y-axis across, that's just x. Oh yeah, but I have to express it using the y variable. So how do I express x using the y variable? Right here, x equals 4 minus y squared. So here that should be 4 minus y squared. Yeah, my apologies, I had those backwards for a second. And then that's integrated with respect to y. Right? So that doesn't change. These describe your boundaries of the original flat region, in this case from 0 up to 2, along the y variable. P of y tells you, okay, from your axis of rotation to the edge of your shell, along the base of the shell. Oh, well that's, using the y variable, I want to know how do I describe going straight up a certain amount. Well, that's just the y variable. But now, from the y-axis, I want to report how far I moved across to get to this point. Oh, well, that's the x variable. All right, but I need to use the y variable to describe that. Oh, so using this equation, x equals 4 minus y squared. And now once we have that, the rest of the problem is just a straightforward computation. Here, let me just distribute the y to get something a little bit nicer. 4y minus y to the third dy. And now I can integrate that without much issue. That's 2 pi integral from 0 to 2 of 2y squared minus y to the fourth over 4. I've already integrated, so I don't need that symbol anymore. from 0 up to 2. Substituting in 0 here does nothing. It gives you 0. But substituting in 2, oh, let's see here. 2 squared is 4 times 2 is 8. Minus 2 to the 4th is 16. Divided by 4 is just 4. And that goes 4 times 2 pi is 8 pi. And there we go. Incidentally, if you took this same region and did it using the disk method, your computation would look different. And in the end, you would still get 8 pi. Assuming you set it up correctly to model this object, the volume you get is the same with either method. The difference will sometimes be one method will be much simpler to use than the other, but the result will still be the same. So let's take a look at another example. Same thing, nothing tricky, nothing unusual, just another example of using the shell method. So this problem gives us not an illustration, but rather a description. It says use the shell method to find the volume of the solid made by revolving the region bound by the graphs of y equals the square root of x, y equals 0, and x equals to 4. And you're revolving that about the line x equals to 6. Okay, so even though we're not given an illustration, it might be a good idea to spend a minute and actually try to at least sketch one out. These equations are not very complicated, so it shouldn't take terribly long to do so. Okay, y equals the square root of x. Well, I know what that is. That's a positive square root, so that's going to be up here. Negative square root's down here, yeah? Okay, so there's my y equals square root of x. Now, y equals to 0, well, that's the x-axis. Okay. And x equals to 4, well, that's a vertical line. That's 4 units to the right of the origin. So that's going to be maybe here. All right. So here's my region. It's the stuff that's bound by all 3 of those lines. Okay, so now we're going to revolve this around a line, and that line is not going to be either the x-axis or the y-axis. Rather, it's going to be the line x equals to 6. Okay, so x equals to 6 is this line out here. It's a little bit further than x equals to 4. And we're going to revolve around that line, which means this will spin around. And we'll end up with this object here. Something like that. So now we're supposed to make an equation. We're supposed to use the equation that we saw before to find the volume of this object. So now remember our equation, our formula tells us that volume using the shell method is 2 pi integral from a to b of p of your variable times h of your variable d your variable. Now in the last example we had p of y, h of y, dy. But notice here that won't be the case because my shells are no longer horizontal. Notice if I have this object and I try to make a horizontal shell, the opening is going to be in the wrong direction. Notice, since I revolved around this line, x equals to 6, these circular cross sections should be facing in that direction, which means that my shells should be facing this way, not this way. But if they're facing this way, that means their thickness is not being measured up and down, it's across this lip right here. Or in other words, it's along the x-axis. So here that's going to be with respect to x. In summary, if the axis of rotation is vertical, straight up and down, whether it be the y-axis or somewhere else, the shell method uses integration with respect to the x variable, with respect to x. So you'll see dx here. On the other hand, if the axis of rotation is horizontal, like we saw in the previous example, either the x-axis or parallel to the x-axis, the shell method uses integration with respect to the y variable. You'll note this is the exact opposite of the disk method. So if the disk method uses the y variable, the shell method will use the x variable. If the disk method uses the x variable, the shell method will use the y variable. They will always be opposites of each other. So in this case, if you were using the shell method, you would use integration with respect to x. On the other hand, if you were using the disk method, this would be integrated with respect to y. All right, so here, let's go ahead and do this one with the shell method with respect to x. All right, so 2 pi is, well, it's just 2 pi. Now remember, this was our original region here before we revolved anything. These boundaries need to describe the extreme x values of the original region. Okay, well, the original region started over here at the origin and went right until we got to 4. Okay, so it's going to be from 0 to 4. Okay, how far up does it go? We don't care. Only the x variable needs to be considered when looking at these boundaries from 0 to 4. Okay, so now my shells look something like this, right? They have this shape. So let's consider the p of x. What I want to do is I want to find the distance from the axis of rotation to some shell that I have. Okay, so let me just say that I have that shell right there. Let's say that one's already the one I'm considering. Okay, well, let's see. Right here, x is equal to 4. So how far is it from this point to the axis of rotation? Now remember, the axis of rotation is not the axis of the x or the y-axis anymore. It's this line right here. Okay, well, if this is x equals to 4, and the axis of rotation is at x equals to 6, the distance is 2. Okay, well, what if I was out here when x was equal to 0? How far is it from x equals to 0 to x equals to 6? Well, that's 6. Okay, well, what if I was right here? What if x was equal to 1? How far is it from x equals to 1 to x equals to 6? Well, that's 5. Well, how are you getting that? Well, I'm subtracting. 6 minus 4, that's the distance 2. 6 minus 1, that's the distance 5. 6 minus 0, that's the distance 6. So it looks like to find the radius of my base, what I need to do is I need to take 6 minus whatever my x variable is. Okay, so p of x is going to be 6 minus my x variable. Note, I have an expression using only the x variable, which confirms that I haven't made any major mistakes. I can only deal with the x variable with this type of rotation. H of x is going to be the height of one of these shells from the bottom to the top. Oh, well, from the bottom to the top, that's just given by the equation. The equation y equals the square root of x, that tells me how far it is from the bottom to the top. Because after all, if x is equal to 4, then the height from here to here is going to be 2. because when x is equal to 4, the height is 2. Okay, so what I need to do is I need to give the distance from the x-axis up to here, which is given by the y variable. Okay, so I could just say y. Well, yeah, but I need to express that with respect to x. Okay, well, this equation tells me what that is. Y equals the square root of x. Note that the integrand is, again, something reasonably straightforward and simple. It's getting this put together in the first place that often takes the greatest amount of time. If it takes you 10 minutes to do one of these problems, that's perfectly normal. And if 8 of those minutes are setting this equation up, that's also perfectly normal. So let's go ahead and go through the final computation. This is the 2 pi times the integral from 0 to 4 of, let me write this as 6 to the 1/2 power, because that's usually easier to work with since I can use the power rule. Let me distribute. 6x to the 1/2 minus x to the 3/2, all integrated with respect to x. And so that's going to be 2 pi times, well, that's x to the 3/2, but then I have to now divide by the new power. So 6, and that's 3/2 like that, minus, and now that's going to be add 1 to the power, so that's 5/2, but then divide by the new power, 5/2, and everything's being evaluated from 0 up to 4. Here, let me simplify that, right? X to the 1/2, the integral is x to the 3/2 over 3/2. Well, yeah, but now I have complex fractions. Let me just clean that up a little bit. If I take 6 and divide by 3/2, I get 4. So that's 4x to the 3/2 minus, dividing by 5/2 will just give me 2/5 x to the 5/2. And again, that's evaluated from 0 up to 4. So now, note that if you plug in 0, that's 0 minus 0, so that's not going to give us anything. So let's just worry about the 4. So it's going to be 2 pi times, let's see, 4 to the 3/2, that's 8, times 4 is 32, minus 2/5. Let's see, 4 to the 5/2, that's 32. And so that's going to give us 2 pi times 32 minus, let's multiply those together, 64/5, like that. Let's see, that'll give us 2 pi times, oh, what would that be, 96/5? Yeah, 96/5. And then we can multiply those together, and that'll give us 192 pi over 5. And that's going to be the volume of that solid of revolution. Just like in the previous sections, since this is a volume, it does have a unit. Since we're not originally given any units of measurement, inches, feet, or miles, we don't exactly know what unit this is. So in absence of any further information, oftentimes we'll say, oh, it's that many units cubed. So we have our result. All right, so go ahead and give this a try. Remember, the computation at the end is usually fairly straightforward. A polynomial, you know, if I'm feeling mean, maybe a simple trig function, but the setup is the one that takes the bulk of the time. So let's see here. Let's give you a region, and let's say here's the region bound by these curves. This is going to be y equals to x squared. This one's going to be the line y equals to, let's say, 2. Okay. And then we're going to revolve around this line out here. Okay. And you know what? Just to make your computation a little simpler, well, no, that's fine. We can just use that. I was going to change that number a little bit, but that's okay. So let's see. Let's go ahead and keep this line, and we'll make it x equals to 3. Okay? So when you take this flat region and revolve it, it's going to look around this line. It's going to look something like this. All right. So you're going to take this region, you're going to revolve it around this line to form this solid of revolution, and you're going to find the volume. So using the shell method, find the volume. Okay. Go ahead and give that a try. Go ahead and pause the video to give yourself as much time as you need. And once you're done, go ahead and unpause the video and we can go through this together. All right, so let's take a look. To find the volume using the shell method, 2 pi, you're going to go from A to B of P of a variable, H of a variable, D of that variable. All right, so first of all, let's talk about what variable of integration we'll need to be using. Note that, as we mentioned before, if the axis of rotation is vertical, then the shell method will use integration with respect to the x variable. So here, that's what we have. We have a vertical line of axis of revolution. So we're going to integrate with respect to x. If that axis of revolution had been horizontal, we would integrate with respect to y. Okay, so now we're going to need to describe this original region, the one that we had before we started revolving, and we're going to describe the extreme values of x on this region. Well, obviously, since it goes all the way to the y-axis, that means that the smallest x value is 0. Up to, now note this is the line y equals to x squared. Now we know we go up to y equals to 2. Well, yeah, but we don't really care about what the y value is. We want to know how far out the x value goes. Okay, so the maximum x value would be here when y is equal to 2. Okay, so 2 equals to x squared, which means we'd either have positive the square root of 2 or negative the square root of 2. Can't be negative since that would be in this quadrant, so it must be the positive. All right, we need x to go from something to something. We can't say from 0 to 2, that's the y value. We need the x value from 0 to, if you say y is equal to 2, okay, then this line tells you that 2 equals x squared, so then x must go up to the square root of 2. Okay. So now p of x and h of x. Here I'm going to go ahead and draw one shell. Again, it doesn't have to be a very good drawing. It's just for the sake of illustration, just to show exactly what it is that we're looking for. So here's one shell. Notice it's a very wide hollow cylinder. It's a very wide hollow shell, but it's still one of these things, right? It's a lot wider than any of the ones we've seen before, and it's a lot shorter. You notice that it's not very tall, but it's still basically one of these things, a hollow, empty shell. Right? So here we're going to take this object and we're going to describe P of x, which gives us the distance from the axis of rotation to the wall of one of these shells. Or in other words, we want this distance from here to here. So let's see. This distance from here to here, and that's going to be our P of x. Well, notice that if we're looking for the distance from here to here, that's simply going to be 3 minus your x value. Because over here, if your x is equal to 0, the distance from 0 to 3, well, that's 3 units. Right here, let's say x is equal to 1. The distance from 1 to 3, well, that's 2 units. You're taking this value minus the x value you have to tell you the distance from that x value to that axis. So here, P of x is going to be 3 minus x. You're going to notice that shows up a lot for the shell method. P of x, if your axis of revolution is not the x-axis or the y-axis, if it's somewhere else, you're going to notice this pattern show up a lot. The axis minus the variable. So, 3 minus x, or in another orientation, 3 minus y, something like that. Okay? That's not guaranteed to happen, but you're going to notice that happen a lot. H of x, well, that's going to be the height of one of these cylinders. And notice that's simply from this y value up to this y value. Okay, but of course we have to express those using the values of x. Okay, well here, this doesn't need to be expressed with respect to x or y. It's a constant. Here, this is always 2. So what I need to do is I need to find the distance between this constant 2 and this curve down here. Well, it's the same thing we just did. Take your constant minus the curve. So that's going to be 2 minus, and now this curve, y equals x squared. Oh yeah, but I have to express it with respect to x. So here, I'm going to write this as just the x squared, like that. That way, if x is equal to 0, 0 squared is 0. And if I subtract 2 minus 0, that gives me the height of 2. Over here, let's say it's 1. X is equal to 1. Okay, well then 1 squared is still 1. And 2 minus 1, that's that distance. Let's say I had the square root of 3. Well, I guess we wouldn't because we only go up to the square root of 2. Let's say we had 0.7. That's fine. If we have x is equal to 0.7, squaring that gives us 0.49, which will give us this height from the x-axis up to that point. And now 2 minus 0.49 gives us the height all the way across. It's going to be the constant minus this curve. And make sure you're describing the curve with respect to the right variable. You shouldn't say y here. You should say x squared. And that's it. That's our setup. We can distribute this now to get 2 pi, integral from 0 to root 2. That's going to be 6 minus 2x minus 3x squared plus x to the third dx. And now this is just a nice simple polynomial. Okay, so let's integrate. This is going to be 2 pi integral from, we're going to integrate now, so we don't need that integral sign. This will be 6x minus x squared minus x to the third plus x to the fourth over 4. And that's going to be evaluated from 0 up to root 2. Obviously, 0 minus 0 minus 0 plus 0 is not going to make a difference. So let's just worry about the root 2. So it's going to be 2 pi times 6 root 2 minus root 2 squared, that's just the number 2, minus root 2 to the third power, that's going to be 2 root 2. Root 2 to the fourth power, that's going to be 4, divided by 4 is just 1. And now some like terms combine. We can write this as 2 pi, 6 root 2 minus 2 root 2, that's 4 root 2, minus 2 plus 1 is just minus 1. And then we can distribute the 2 pi to get our result. We can write this as 8 root 2 minus 2 times pi. Again, we're talking a volume, so this is going to be in units cubed. Cube inches, cubic feet, cubic miles. We don't know what those units are, so typically we just say units cubed. And there we go. All right, so as our last example, let's take a look at one more, and let's talk about why the shell method is necessary. After all, in the last section, we learned the disk method, the washer method, and those methods together gave us everything we needed. Right? We were able to find any volume. So why do we need another method? Well, it turns out that depending on the equation, the disk washer method may not be nice, or in some cases, it may not even be feasible. So let's consider the following example. We're going to find the volume of the solid. Formed by revolving the region bound by the graphs of y equals x to the third plus x plus 1, y equals 1, and x equals 1. And we're going to revolve that around the line x equals to 2. Okay. And here, they don't tell you to use the shell method or the disk method. They just say find the volume. Okay, that's fine. Here, they don't give us an illustration, but we can illustrate that ourselves. Oh, actually, I take that back. They do give us an illustration down at the bottom of the page. So here we have an illustration that looks like this. All right, so here we have 1, and here we have 1. And there's our region. So it's bound between y equals to 1, x equals to 1, and y equals x to the third plus x plus 1. So that's this curve here. Okay, so now we're going to revolve this around the line x equals to 2. Okay, so here's the line x equals to 2. Okay. All right, so now let's say we wanted to use the disk method. We say, well, you can't, because look, there's a hollow gap in the middle. Okay, well, that's fine. That means we need to use the washer method. All right, so right off the bat, the disk method cannot be used. Why? Because the region does not go all the way to the axis of rotation. There's going to be some space in here, which means there's going to be a big gap in the middle. So the disk method will not work because we know there's empty space in the middle. Okay, so either the washer method or the shell method. Okay, that's fine. Now, why don't we try the washer method? Okay, well, let's give that a try. We know that the axis of rotation here is vertical. So that means, in fact, let's write that down. Since the axis of rotation is vertical, the washer method will look like this. It'll say volume is equal to pi integral of, we're going to take a function of y squared minus a function of y squared dy. So because the axis of rotation is vertical, the washer method has a function with respect to y. The shell method tells us that the volume is going to be 2 pi times the integral from a to b of p of x h of x dx. The washer disk method will always use the opposite variable as the shell method for any given illustration. So if this one's using y, that one will use x. If this one's using x, that one will use y. Okay, so what? What's the problem? I have an equation here. I just substitute in whatever I like. Okay, so then let me just pick one and do it, right? Well, here it's not quite that simple. Let's say I try to use the washer method. Okay, so then that means I'm going to take volume is equal to pi times the integral from a to b of f of y quantity squared minus g of y quantity squared dy. Okay, so now remember, f of y is simply the biggest radius of any disk. So right here, we're slicing this way. Each of our disks are stacked right on top of each other. We have the biggest disk on the bottom, and they're getting smaller and smaller until you get to the top. And I guess I'm using the wrong word. It's not a disc, it's a washer because there's a hole in the middle. So here I have these washers stacked, the biggest ones on the bottom, and they get smaller and smaller until you get to the top. Okay, so then that means that the radius is just going to be the distance from here to this outer curve. Now remember, it all has to be expressed with respect to y. So what that means is I need to use this curve, but I need to express it with respect to y. Okay, so all that means is I need to write this curve as a function of y. I need to write, instead of y equals a function of x, I need to write x equals a function of y. All right. If you want to try to do that, go ahead, pause the video and see if you can do that. See if you can invert this so that instead of saying y equals a function of x, go ahead and try to isolate x. Right? Once you have reached some kind of conclusion, go ahead and unpause the video and we can go through it together. Okay, so hopefully you won't be too terribly mad, or you didn't spend too terribly long doing this. This is an extremely difficult problem. Isolating x in this one is not something I'm actually going to try. Is it doable? It actually is doable. You can isolate that. It's not a simple procedure. And it's definitely not something that's worth your time doing. Here, the reason why we have the shell method is because sometimes the disk washer method has the function in such a way that isolating the remaining variable is difficult, if not impossible. For those of you who actually did pause the video and try it, you'll note just how long and complicated that was. For those of you who actually reached the conclusion, very good. That means that your algebra is very, very strong. But if you didn't reach a conclusion, if you weren't able to isolate x, don't worry too much about it. It's not something we would reasonably expect you to do in a short amount of time anyway. So here, what we want to do is we want to say, okay, since this is either difficult or impossible, and in some cases it actually is impossible to invert them, let's go ahead and use the other method here, the shell method. So here I'm going to just say not nice. Okay. The shell method would have us do it the other way. It would say, okay, volume is equal to 2 pi integral from a to b of p of x h of y, p of x h of x dx. Okay, here this function was difficult to write in terms of y. Okay, so how do I get it in terms of x? Well, it's already in terms of x. So things are nice here. So here, let's go ahead and set that up. Volume is equal to 2 pi integral from. In fact, you might want to try this. If you, again, if you're not still too tired from having tried this, if you did, go ahead and pause the video and give this a try. See if you can go through. And now that you know that the shell method is the one to use, it actually isn't too big of a problem. Go ahead and give this a try, see if you can set that up, and then once you have your result, go ahead and unpause the video, and we'll come back and do it together. All right, so we know we're integrating with respect to x, so everything needs to be done with respect to that variable. Okay, so right here, my variable goes from 0 to 1. All right, I care about where my x variable is bounded. Yes, I know my y variable starts from 1 and it goes up higher. We don't care about y for this computation. We care about x. From here to here is my original region. So that's from 0 to 1. P of x is the average radius of one of my shells. So that's going to be this distance from the axis of rotation out to my shell. Notice that is starting from 2 going backwards. So as I mentioned, you're going to see this a lot. That's going to be 2 minus your x value. Oh, if x happens to be 0, 2 minus 0, that's 2. That's that distance there. If I'm at a half, 2 minus a half, well, that's 1.5. That's the distance from here to here. That'll give me the radius of one of these shells. h of x is the height of one of these shells from here to here. And that's just going to be from this curve up here, which I already know the equation of in terms of x, right? It's already in terms of x. But then it's going to go down, not all the way down to the x-axis, but down to 1. Okay, so take this curve, which would give you the distance from here down to the x-axis, and then subtract 1 so that I don't have to worry about this part down here. So this would be x to the third plus x plus 1. That's my curve. But then minus 1. Because again, notice it doesn't go all the way down. Right? From here to here, if this was 2 units long, I don't want to go all the way down 2 units. I want to go down just this amount, which is just 1 unit. So I need to subtract this extra 1 down here. Okay, so now we can write that as 2 pi, the integral from 0 to 2 of 2 minus x times, since these two just subtract away, we can write that as x to the third plus x, just like that. And now we can distribute that stuff to give us 2 pi, the integral from 0 to 2 of, oh, let's see here, that's going to be negative x to the fourth, and then that's going to be plus 2x to the third, minus x squared, and plus 2x. Looks like that. And now we can integrate and get our result. Notice that the setup tends to be the harder part. Once you have everything set up, the integrals are going to be generally nice and straightforward. So this is going to be 2 pi times negative x to the fifth over 5 plus x to the 4 over 2 minus x to the third over 3 plus x squared, evaluated from 0 up to 2. Obviously, substituting in 0 makes all of these 0. So 0 plus 0 minus 0 plus 0, that's not going to matter. Let's just worry about plugging in the number 2. So that's 2 pi. Let's see, 2 to the fifth is 32. So that's negative 32 over 5 plus 2 to the fourth is 16, but divide that by 2 is 8, minus 2 to the third is 8, and that's going to be over 3. Let's see here. Oh, my apologies. How did that become the number 2? It was from 0 to 1. I don't know how that became the number 2. There we go. So I'm plugging in the wrong number here. 1 to the fifth power is just 1. In fact, all of those are just 1, aren't they? Let's try that again. Negative, that's going to be 1 to the fifth power. Here, that's going to be 1 over 2. That's going to be 1 over 3. And then that's just 1 squared, which is the number 1. All right. So now we can put these together and give them a common denominator of 30. And that'll give us, let's see. You can write that as what? 2 pi. Let's see, if I'm putting everything over 30, that's going to be negative 6 over 30 plus 15 over 30 minus 10 over 30 plus 30 over 30. So 35, 29 over 30. Yeah. So this will give us 29 over 30, but then you're multiplying that by 2 pi. And then here these divide away. 2 goes into 30 15 times, and that gives us 29 pi over 15. And again, this is the volume, so this is going to be units cubed. Cubic units, units cubed, however you want to say that. There's several ways to say that. Some people will even write units with a little third power on top. You can say cubic units. You can say units cubed. Some people like to write units cubed like that. Any of those are fine. And there's our result. So this brings us to the end of our section. To summarize, make sure that you remember this right here. This is the thing that most people will have a hard time with, and that is getting your orientation correctly. For the shell method, the axis of rotation being vertical means you're integrating with respect to x. Horizontal means you're integrating with respect to y. When you compare the shell method to the disk washer method, those are always opposites. If the washer method uses the y variable, then for this example, the shell method will use the x variable. If in a different example, the washer method used the x variable, the shell method will use the y variable. Make sure you keep those straight because those are the biggest sources of confusion and problems for using the disks, shell, and washer methods. So that brings us to the end of this problem and the end of this section. If anybody has any questions, comments, or problems, please make a note of those and let me know. Reach out to me during office hours or during our next class meeting. And I hope everyone has a nice day.